Welcome back to IT 3000. Today, episode 16, the device driver. Think of it as a translator. Your operating system knows, in the abstract, what a disk is, a thing you read from and write to, but only the driver knows what your specific disk actually is and how to speak its particular dialect. So let's pin down the concept a little more precisely. A device driver is the software layer that takes the operating system's generic requests, read this block, write these bytes, and turns them into the very specific commands your particular piece of hardware actually understands. Then it takes the hardware's response and reshapes it back into the form the OS was expecting. One language up top, one dialect down below, and the driver sitting in the middle doing the translation both ways. Now, Unix takes an interesting approach to organizing all these translators. It exposes most devices as files, and the way that file behaves is really what sorts drivers into classes. Character devices are pure byte streams, think keyboards or serial ports, where you just read what shows up in order. Block devices deal in fixed-size chunks with random access, buffered by the kernel. That's your disks and SSDs. Network devices break the file metaphor entirely. Packets flow through the network stack instead. And finally, bus and virtual drivers cover things like USB and PCI controllers, plus purely software constructs like dev null. So how does one of these translators actually live inside the kernel? A driver isn't a program you launch. It's a set of callbacks the kernel reaches for at specific moments. It starts with probe, when the bus announces a device, then initialize, where it claims resources and registers its handlers, then the long operate phase, serving requests and handling interrupts, suspend and resume save and restore state around sleep, and remove cleans everything up. And here's the quiet truth. Most driver bugs don't hide in the busy operate step. They live in the rare paths, resume and remove, the ones almost nobody exercises. Let's watch those callbacks in action. You push a USB stick into a port, and for maybe 4 seconds nothing seems to happen, but underneath, 5 layers are handing off a baton. The hub sees a voltage change and interrupts the host controller. The USB core reads the descriptors, vendor ID, product ID, device class. The kernel matches those IDs against every registered driver, and the mass storage driver raises its hand. It registers a block device, the file system mounts it, and a new disk quietly appears. Notice what didn't happen. Nothing above the driver ever needed to know the word USB. That's the translator doing its job. Now here's a subtlety worth pinning down. That same translation job can live in 3 very different places. The classic spot is inside the kernel, ring 0, full privilege, fastest ordinary path, but one bug and the whole machine goes with it. Move the driver into user space, think Fuse, libUSB, most printer drivers, and a crash only takes down one process. You pay for that safety with extra transitions across the kernel boundary. And then there's kernel bypass, DPDK, SPDK, RDMA. The application maps the device straight into its own memory and talks to it directly. Fastest of all, but you've just handed back the protection and sharing the OS was giving you. If this idea of the driver as a translator caught your attention, there's a whole neighborhood of concepts sitting right next to it. Kernel modules are how you plug a driver into Linux without rebuilding the whole kernel. DMA is how devices move data without bothering the CPU. PCIe and USB are the buses those devices actually sit on. Firmware is the tiny code running inside the device itself, and the HAL is the layer that hides the messy hardware differences from everything above. Each one is worth its own episode, and next up we cross into the file system. So let's leave you with 3 things worth remembering. The 4 driver classes, character, block, network, bus, and virtual, are defined by behavior, not by the physical device. A driver itself is really just a set of callbacks with a life cycle, and it's the rare paths, not the busy ones, that tend to break. And above all, everything above the driver is portable, everything below it isn't. Holding that line is the driver's entire purpose, the translator between one device and everything else. See you in the next episode.